is Formula 6 at Pakistan. So I'll start the webinar. Hello, everyone, and welcome to the second installment of our seminar series on models, learning, and sensing in hydrology. The main idea behind this series is to highlight the recent advancements in hydrology through numerical modeling, machine learning, and remote sensing by significant contributors of terrestrial hydrology in particular. It is a great honor for me to introduce today's speaker, Dr. Bart Foreman. He's an associate professor at the University of Maryland in the Department of Civil and Environmental Engineering. Dr. Foreman has worked extensively with NASA on their terrestrial water and advanced technology initiatives. Dr. Foreman was also a Fulbright scholar to India and is actively involved with Engineers Without Borders. The list of his accomplishments encompass research as well as social initiatives. Today, Dr. Foreman will be talking about the optimal mixture of space-borne sensors for remote sensing of terrestrial freshwater through a comparative analysis of passive optical, passive microwave, active microwave, and LiDAR retrievals. Thank you for joining us today, Dr. Foreman. We are very happy to host you. There will be a question and answer session at the end. If the audience members have any questions, please feel free to write them in the chat box or send them directly to me. With that, let's begin our talk. And Dr. Foreman, the floor is yours.
Thank you very much. I'm honored to be here. Good evening, everybody. My name is Bart. I will attempt to share my screen. And in about 10 seconds, hopefully you can see it. I'm going to be talking about mostly passive microwave, active microwave, and LiDAR as a means of combining these different instruments in order to, quote unquote, optimally retrieve land surface hydrology signals. It's going to be a focus on soil moisture, vegetation, and snow. And I want to highlight many of my partners on this. Sujay Kumar down the road at NASA Goddard, he and I are taking the lead on this. He has a wonderful team, all working with the NASA Land Information System that I'll talk about later. Dr. Paul Grogan up at Stevens Institute in New Jersey is an aerospace and systems engineer that's helping us with some of the orbital configurations of these satellites. And then a slew of postdocs and graduate students also contributing. So hopefully this video appears somewhat clear on your end, but what we're looking at is a video of the hydrologic cycle. Sun comes up, we begin to get some evaporation, we get some rising of those molecules, they expand adiabatically, hence they cool, we get condensation, eventually we get collision and coalescence of those particles into larger and larger particles. And now the water cycle returns to the Earth's surface either in a liquid or solid phase, highly complex, highly dynamic in space and time, highly nonlinear. In this particular project, we're going to focus mostly on what's going at the land surface. It's going to be a focus on snow up in the mountains, or soil moisture lower in the valley, and then the vegetation that is growing seasonally throughout. We, of course, have latent and evaporative heat fluxes from the land surface in our system, and we have runoff, and we have shallow groundwater, and we have everything that we see here. Again, a very highly complex, highly dynamic system. And the question is, how do we view this? What is the best way to make measurements of this system? Very often, snow is studied independently from soil moisture or vegetation, or soil moisture is studied independently from snow or vegetation. Often one of these three components is studied independently from the other two. But in reality, if we want to make measurements from space and say make measurements of soil moisture, we need to know something about the overlying vegetation over that soil moisture, because the vegetation can be noise in our signal. Or we need to know something about the snow that is overlying the soil moisture. If the soil is frozen or partially frozen, our sensors in space may not be able to retrieve the soil moisture that we care about. So if we want to study one, we often need a priori knowledge of the two. And so what we're trying to do in this project, not only figure out the best way to view and quantify these different stores in the hydrologic cycle, but how to do it all simultaneously in a fully integrated and cohesive format. So the second video that I'm showing, again, I apologize if it's not clear on your end, but what I'm showing you are two different versions of the Earth, and each version of the Earth has a series of satellites in orbit. I'm going to focus on passive microwave radiometry, which is a relatively wide field of view. These are not the scale, but imagine the green dot can see more of the Earth at an instant, or synthetic aperture radar as shown in red, or optical LiDAR as shown in blue. We can use passive microradiometry to study snow and soil moisture. We can use synthetic aperture radar to study snow, soil moisture, and vegetation. We can use optical LiDAR to study snow and vegetation. So one of these instruments can be used for more than one of these state variables that we care about. And the question becomes, how do we mix and match these different sensors? Should we just use all passive microwave radiometers? Should we just use all synthetic aperture radar? Should we use only LiDAR, or should we mix and match? Should we have 3 radiometers or 4 radiometers? Do we need 1 radar or more than 1 radar? And it's not just the number of the sensors that we need in order to achieve some scientific benchmark, but it's also the coordination of those sensors. What orbital characteristics? Should it be polar orbiting sun synchronous? Polar orbiting non-sun synchronous? Should it be a highly inclined orbit, or should it be a low inclination orbit? Should we run them independently from one another, or as we see here, I have a scenario where arbitrarily I've taken a passive microwave radiometer and a LiDAR, and I've linked them together in an A-train type configuration. Should we run them in tandem, or should we run them independently? How many do we need, and for what reason? What orbital configuration? What air characteristics? What field of view? On and on and on. There's many, many degrees of freedom in this highly dimensional problem in order to figure out what is the optical mixture. And just to make things more complicated, one mixture of sensors, maybe we are focused on snow. And so we want those sensors to preferentially view snow-covered areas. Or maybe we are interested in vegetation, in this case, change in vegetation. We may want a different mixture of sensors if we care most about vegetation. Or here in the lower right, I'm showing irrigated areas. Perhaps we care more about soil moisture, and particularly soil moisture in the irrigated areas with high dollar agricultural crops. We may need a completely different mixture of sensors in space and time to optimally view these. The question becomes, how do we do snow, soil moisture, and vegetation simultaneously in the most efficient and optimal format? So terrestrial freshwater, as we all know, highly dynamic, coupled, changes rapidly in space and time, and it's nonlinear. In order to study the snow, soil moisture, vegetation system, we really need a cohesive and physically consistent framework. And we're going to use the NASA Land Information System to do that. In addition, we're going to leverage a suite of remotely sensed observations. Most of what I talk about today is just going to be related to LiDAR, passive microwave radiometry, and active microwave, in particular, synthetic aperture radar. But part of this project, we're also including visible and near infrared imagery as related to perhaps snow albedo or leaf area index for vegetation. So there's more to this project than I'm presenting, but we are looking at more than one type of observation. When we think about this cohesive system, when we think about all these different observations, what we really need is an observing systems simulation experiment, or an OSSE. This is purely computational, it's purely synthetic, but what we try to do is we try to come up with a very good computer-generated version of the natural environment, very good computer-generated version of space-borne retrievals, and then we try to merge our model and our observations together to make something that's better than either the model or the observations alone. And so we're going to do this through an OSSI, and we're going to run a series of experiments. I will briefly talk about data assimilation. Professor Dara Entakabi, who I know is your first speaker, has done some really foundational groundbreaking work on this, and he was a huge impact. He had a profound impact on my philosophy when I was a graduate student learning this material. So I'm going to stand on the shoulders of giants and borrow from them. We're going to use data assimilation to merge our model and observation, hoping that we can improve the coupled snow, soil, moisture, vegetation response. So the starting place for this is the NASA Land Information System. Most people think of this as a model, but it's much, much more than a model. We do have a model, and we have many different models that we can choose from. But if we look at this graphic in the lower left, the black box, the black line represents the model domain. And then we apply our boundary conditions of energy and mass, and then we can solve the conservation of energy, conservation of mass, conservation of momentum equations internally. And we get our runoff and our groundwater and our soil. So we have a land surface model and more than one that we can choose from, but in addition to that, list is much, much more. It has all of the observational data, be it satellite or ground-based, different modeling techniques. We have optimization routines, uncertainty estimation routines, of course, the data assimilation. We have a series of different land surface models. This list that you are seeing is actually outdated. There's many more models in here. And in particular, we've been on separate projects, Crocus, the Crocus snow model, and a different snow model with the very apt name snow model, Glenn Liston's snow model, who's a distinguished professor at Colorado State. He has one of the best snow models, in my opinion, in the world. And this too has now been integrated in the list. So we're getting more sophisticated physics. We're being able to resolve processes at finer and final spatial and temporal scales. And we can choose the right model that we need for our particular application. So we've got the land information system. This is sort of at the core of our experiment. In addition, we're going to have a number of geophysical retrievals. I mentioned I'm going to be focusing on passive microwave radiometry, synthetic aperture radar, and LiDAR. We have many different spectral bands that we can choose from that can be used to derive snow water equivalent retrievals or soil moisture retrievals within the top centimeter. Perhaps we use L-band radiometry. Professor Entakabi, I'm sure, was talking quite a bit about the use of L-band radiometry and some of the profound impacts it's had on global soil moisture estimation within the top 5 centimeters. It can also be used for vegetation optical depth. So these different sensors, be it radiometry, SAR, LiDAR, we can measure more than one state variable that we might care about. In addition, many of these sensors actually do not exist. There is no space-borne snow LiDAR. But we have a number of different proxies that we can use in order to scale up on our calculations of volume, weight, and power requirements. Not only are we looking at the sensor, but we're also considering the type of propulsion system we need in order to inject these sensors into orbit. So if it's a big, heavy sensor, we need a big, heavy rocket and lots of money. Or maybe we could use a series of smaller, lower accuracy CubeSats, requires a smaller, cheaper rocket in order to install these sensors into space. And so we were able to use some of these proxies and upscaled as needed for some of these cost estimate calculations. So we've got a sophisticated land surface modeling system. We have a number of retrievals. And when we think about these retrievals, there's a very large trade-off space that we need to consider. So in this upper left figure, FOV, this stands for field of view. So we could have a field of view arbitrarily at 15 degrees or 30 degrees or 45 degrees. As that field of view gets bigger, the effective swath width of the satellite gets bigger, and the satellite will see more of the surface with regularity. But there may be a trade-off. A larger field of view may give you a coarser resolution product, or perhaps a lower accuracy product, depending on the particular sensor design. But just thinking about the space-time coverage, what I'm showing you here is revisit time. So we would like a short revisit time so we can see the Earth all over with more regularity. And a larger field of view will bring that revisit time down, but there is a trade-off. And of course, as we increase the number of satellites, maybe with 1 satellite or 2 satellites or 3 satellites, if we increase that number, we can reduce the revisit time. Of course, there is a trade-off and there is an additional cost. And not just the sensor itself, but the platform. We can change the altitude. We could fly the platform relatively close to the surface. We are constrained by Newtonian kinematics, so these are not all perfectly feasible. Some may require propulsion systems to make small altitude adjustments, but ignoring that, imagine close to the surface or further away from the surface. Close to the surface, it'll take more time to revisit. As we move away from the surface, we can effectively see more at a given time, so we can revisit at a faster rate, add the number of satellites, and we can see more and more and more. I'm sorry, this is instrument elevation angle. This is not number of satellites, I apologize. But there's a number of design considerations: field of view, altitude, instrument angle, the type of orbit. And then beyond that, there's also low accuracy sensors. Do we want to spend relatively little money to get a low accuracy sensor, or should we put all of our eggs in one basket, build a large monolith with very, very high accuracy? And what's the trade-off there? Do we want one platform, or do we want a constellation? Do we want sun synchronous polar orbiting, non-sun synchronous? Do we want a more a lower inclination orbit, more akin to, say, the International Space Station? Which orbit, number of platforms, altitude, field of view, what's the ideal combination? And ultimately, how do we get the most scientific bang for our scientific buck? If we define some scientific benchmark that we want to achieve, what mixture of satellites and sensors do we need in order to achieve that benchmark? And is there one combination that is less expensive than the other? The final one perhaps is our best choice to move forward with some sort of design in the future. And as if things are not complicated enough, we decided to add one more layer of complexity. So traditionally, instruments have, say, a fixed look angle. Maybe they are looking directly down, or maybe they are looking off nadir. The US Defense Department has had for decades the ability to adaptively turn these satellites or slew the satellites. But this has not been very common practice in Earth system science. But with a lot of these commercial satellite providers setting up systems of smaller CubeSats that can slew the satellite, and if given enough time in advance, the satellite could slew and actually capture the target that we care more about, rather than just missing it with some sort of fixed look angle. So a good sort of canonical example, imagine we have some forest area, and maybe there's been a recent forest fire, or maybe there's been some recent logging, and all of a sudden we have no vegetation. And of course, the partitioning of energy and mass at the land surface will be very different after this fire, or very different after this logging operation. And with the fixed viewing shown in red, well, we might see a little bit of that burn scar, or we might see a little bit of that logging operation. But if we could turn or slew the sensor ever so slightly, perhaps we could preferentially view the areas that have more hydrological value to us and could be perhaps more beneficial in our model. So we can run some experiments with the fixed look angle, and then we can allow the satellite to slew, the sensor to turn left or right so that it can preferentially see the area we care about. And we can run these two different scenarios and see if the adaptive viewing is giving us more information for that extra complexity. Of course, the air characteristics might change too, so that could be part of the trade-off. The adaptive viewing is able to move, but it may encounter higher errors, particularly if it's looking further and further off nadir. So we can do this kind of analysis for forest or vegetation. We could do something similar for snow and ice applications. We know a priori that snow and ice is generally at higher altitudes. Well, if we designed a system that preferentially viewed higher altitudes, maybe we could see more of that snow and ice than if we had a fixed look angle. Or we could do a different approach for snow. Maybe we took some sort of climatology, and we know that a priori there's more snow at higher latitudes and there's more snow at higher elevations. Perhaps we could direct our satellites to preferentially look at these areas rather than focusing on Florida or Texas, where we know there's little or no snow. And we could do something similar for soil moisture. Here I'm showing a map of irrigated areas. Maybe we want to preferentially view the areas that we know irrigation is going on. So maybe we can get more useful information related to soil moisture and vegetation at the same time. So there's a number of different features that we're all trying to bring together into this experiment to try to decide what is the best way to move forward with a next generation system for terrestrial hydrology remote sensing. So talking again about this coordination, I've talked a little bit about field of view and sensor characteristics and orbital configuration, but I want to reiterate again, we may have a very different set of sensors if we want to, say, preferentially view snow and ice at higher elevation. Or we may want a very different set of sensors to preferentially view snow climatology. Or we may want a very different set of sensors related to some change in forest cover or some change in vegetation that hydrologically would be of significant relevance. But we might end up with a different set of sensors, similarly for soil moisture applications. We may end up with a different set of sensors, but we're only going to get one shot at this. And we need to find a set of sensors that work well for snow, for vegetation, as well as soil moisture. So we're trying to find a one-size-fits-all, even though we know that does not exist. But we're going to try to get as close to it as we can. Finally, the way that we bring all of this together, perhaps Professor Antakabi talked about this in more detail than I will, but we're going to be using an ensemble Kalman filter where we run our model. Here we may have some state variable estimate of snow water equivalent. We could do the same thing for soil moisture, the same thing for vegetation. And then we're ultimately going to update or try to improve our model by incorporating information from our measurements. And then we have a computed error covariance structure manifested in these matrices that make up the Kalman gain matrix. But suffice it to say, we can run an experiment with no measurements, see how it performs. Then we can run an experiment, say, only using a single snow LiDAR, see how it performs. Run another experiment, run a snow LiDAR and a synthetic aperture radar, or LiDAR, radar, and radiometry. And we mix and match, run an experiment with low accuracy, run another experiment with high accuracy. Try to find a good combination that achieves the desired scientific benchmark while also minimizing mission cost and mission risk. So as kind of sort of a recap of where we are, what are the objectives here? What observational records are needed in space and time to maximize the couple's snow, soil, moisture, vegetation utility? And further, how might these observations be coordinated? Do we run them in an A train, or should they be separate and independent from one another? Do we need one sensor, or are we better off with a constellation of lower cost, smaller CubeSats? This third question is of very significant importance to NASA program managers. What is the additional utility associated with an additional observation? If we had 3 LiDARs, what could we do? What if we had 4 LiDARs? What if we had 5 LiDARs? What if we had 6 LiDARs? It's a tremendous amount of money, but let's just play these experiments out and ask these questions. There's going to be a break point where really one extra LiDAR is going to have little or no value. But we would like to know exactly what that is and where it happens. And this makes it easy for the NASA program managers to go to Congress and say, we need 3 LiDAR because we know it's much, much better than 2, but it's not so much better if we have 4. So we need 3. How can future mission costs be minimized while ensuring the science requirements are fulfilled? And also risk is in this. If we put all of our eggs in one basket and there's an issue on launch and the satellite doesn't make it into orbit, we've lost everything. If we have a constellation of smaller, cheaper CubeSats, well, 2 or 3 of those may not work, but we could still have 12 or 15 in orbit. So it reduces the risk. All right, I'm trying to get my slide to advance. Here we go. Okay, so let me set up the Observing System Simulation Experiment, or the OSSI. So the first thing we do is we run our best model, best boundary conditions, best everything, and we call it a nature run. Now, this is not exactly the truth, but it serves as a very good proxy. It does not have to reproduce the truth, but it does have to capture the true variability of the system. And this does just that. So we have a very good model. It's not the truth, but it's a very good proxy for the true variability of the system. And within this nature run, we of course have snow, soil moisture, vegetation, runoff, latent heat flux, groundwater. We have everything. We're going to focus on these 4. Then we're going to link it to something called the Trade Space Analysis Tool Constellations. I refer to this as a space-time cookie cutter. This is our nature run, but if we look at what the satellite sees, it only sees a portion of the domain at any point in time. And if we have a different sensor, instead of a wide field of view passive microwave radiometer, well, maybe we have a pencil beam LiDAR. Or maybe we have a relatively wider width synthetic aperture radar. We can get measurements of vegetation, soil moisture, and snow from radiometers, LiDAR, and radars using the same approach. And we'll have different permutations of orbits, different permutations of sensors. And then we will add some error and upscale as needed in space or time in order to come up with a geophysical retrieval, or what we call as our synthetic observations. So at this point, we have a reasonable representation of an observation, which is a subset of the truth system. It's not exactly the same as the truth system, and it has some error, because all measurements have some error. But now we have our truth, quote unquote, and we have our observations. And now we're going to go back to the beginning, and we're going to run a different model. We're going to use a different land surface model. We're going to use different boundary conditions. You can see in these graphics that this is snow water equivalent over North America for the same day. But you'll see that with different models and different boundary conditions, we do get differences. And the differences between these two, we treat as a proxy for real world error. Again, the differences between these two are a proxy for the error. We have errors in snow, we have errors in soil moisture, we have errors in vegetation, we have errors in runoff, everything. The next step is do nothing. We're going to skip the assimilation phase, and we just call this the open loop. And then we're going to run our benchmark evaluation using something that we'll call the land validation toolkit. We'll compare soil moisture versus soil moisture, snow versus soil snow, vegetation versus vegetation, runoff versus runoff. We'll run all sorts of statistics across space and time, and we will see exactly how far from the truth our open loop is. At this point, we have a benchmark for how good or bad we're doing. And now we're going to go back, and now we're going to bring these retrievals into our system. We're going to turn on the assimilation. We can run an experiment with a L-band radiometer, see how soil moisture assimilation does, compare that back to the benchmark. Or maybe we run an experiment with 4 snow LiDARs, run the assimilation, compare that back to the benchmark, and we run experiment after experiment after experiment, and we see how close we can get to recovering the truth. Do our observations really help us get closer to the truth, or do our observations add little or no value to our updated model estimate? So this is the general framework for an OSSI, all run within the NASA land information system. Okay, so the first step is the nature run. And we spent a lot of time on the nature run. Melissa Resran, this is this actually just came out last month. I need to update this slide. I apologize. But in the Journal of Hydrometeorology, Melissa really spent a lot of time talking about the nature run, comparing it against ground-based observations, showing that it's not the truth, but it serves as an excellent proxy for the real-world system, and that it was, in fact, capturing the true variability of the natural system. So we felt really good about the nature. And after that, we linked it up with TAT-C, or our Spacetime cookie cutter. And you can see here that in North America, we have a lot of snow. I'm sorry, this is vegetation in the upper left, snow in the lower left. But there's a lot of vegetation, but of course, the LiDAR does not see everywhere at all times. It's a relatively narrow beam. In this particular scenario, it's not relatively narrow. It's a very, very wide hypothetical beam. But compared to radiometry or SAR, LiDAR is very, very narrow. Plus, LiDAR in this case is optical, so it does not see through the clouds. I apologize, the video has locked up on my end. Here we go. So you can see the observations are not everywhere at all times, but we do have some observations. Snow in the lower left, we see even less observations. That's because there's no snow in the lower United States, only in Canada, but serves as real world proxy for observations. Here we can see L-band radiometry for soil moisture. It's a wide field of view. We have some masking for frozen and partially frozen soils. The radiative transfer models used to do these retrievals generally do not work in frozen or partially frozen soils. So we have to mask all of that out in order to yield a reasonable proxy for that soil moisture retrieval. You can see that the summer is encroaching, soils are thawing out, and now we're able to get some retrievals in these northern regions of Canada when we could not in December. And down in the lower right, when the snow season comes back around, we'll see that we also have passive microwave radiometry derived for sweep. So at this point, we have our notion of a nature run or synthetic truth. And then we've taken our space-time cookie cutter and we've come up with a series of synthetic retrievals. We have these for all sorts of different orbital configurations. We have high accuracy retrievals, medium accuracy retrievals, low accuracy retrievals. So we'll do this exercise for different orbital configurations, and we'll also do it for different error assumptions. Now let's look at some results. So we run this experiment, and here I'm only going to focus on snow water equivalents. And what I'm showing from a multi-year simulation, these are the monthly average snow water equivalent root mean square error. And these statistics are computed.
Dr. Foreman, sorry to cut you.
Yes.
Now, your screen had stuck a little bit, but now it's moved on, so we're good to go.
Okay, thank you for that. So I do apologize for some of the latency. So hopefully you are seeing my bar plot. And right now there's only blue bars. And that is a comparison between the open loop, that is the bad model with no assimilation. This is sort of our proxy for a modeling system with real world errors. And we've compared this against a synthetic truth. I'm only showing you snow, but we have this for soil moisture, vegetation, runoff, latent sensible heat fluxes. We have the entire hydrologic cycle. And this gives us a benchmark or an estimate for how far off the truth are we. Now let's run an experiment. Let's assume we have a single C-band synthetic aperture radar instrument, quite similar to the European Space Agency's Sentinel-1 program. Yes, Sentinel-1. And we can see some very large improvements. We take these observations, we assimilate them into our model using an ensemble Kalman filter, and we can see some significant improvements, particularly during the months when we have a lot of snow. We see little or no change in September, October, November, but that makes sense. There's not a lot of snow in this domain in September, October, November, and we have little or no, we have no snow in this particular domain. I should also say that this particular subset of results, this is not North America as what I was showing in some of the videos. This is actually only a portion of Western Colorado. It's a large domain, but we could not run all of North America. It was just too computationally expensive. So we had to do this over a smaller domain. But suffice it to say, this framework could be run globally if we had enough processors and we had enough time. So back to these experiments, we've run one and we can see, wow, synthetic aperture radar for this particular orbital configuration, for this particular assumption of retrieval errors, we see some significant improvement. Let's run another experiment. Different sensor. Let's take an optical LiDAR, a single LiDAR, and in this case, we're using a 70-kilometer wide swath. This is hypothetical. This does not exist. I do not think we would ever launch something like this. The power requirements would be so great that we would need so many amplifiers that it would be just too heavy. It would be cost prohibitive. But with these Aussies, we can ask this question. What if we had a 6-kilometer swath or a 20-kilometer swath or an unrealistically wide 70-kilometer swath? Well, we don't see a whole lot of improvement, but we do see some improvements, particularly near the peak snow season. So we run our LiDAR, not so great, but things got better. Let's run a different experiment. Let's take our KAUX band from passive microwave radiometer, assume that we have some sort of a SWE retrieval. This is a relatively high accuracy SWE retrieval. This is maybe overly optimistic. We ran similar experiments with larger errors. We see smaller improvements, of course, but this is only one experiment and we see some improvements. Again, most of the improvements are late in the snow season, little or no improvements when there's little or no snow. Better than LiDAR, but not quite as good as the SAR. All right, well, what if we had two LiDARs? What if? We get some improvements, but again, not that much. And we're really talking about a ridiculous sum of money to ever do something like this. So this probably isn't gonna happen, but at least we know what the return value is. Okay, let's run another experiment. Let's take a single C-band SAR and let's blend it simultaneously with the optical LiDAR. Let's put both in space. And now we see something really nice. We see that the combination of C-band SAR and optical LiDAR is better than either the combination of the LiDAR or the SAR alone. These two play nice together. They're both relatively high resolution. They are complementary. This was a very nice result. So we ran another experiment. We took the same C-band SAR, we took the same optical LiDAR, and we put a passive microwave radiometer in space. Surely 3 instruments is better than 2. But no, it's not. The passive microwave radiometer in this case actually made things worse. That's because we were doing this study in a region of complex terrain, and the passive microwave radiometer is on the order of 25 by 25 kilometers, very coarse scale resolution. Whereas the C-band SAR or the optical LiDAR are on the order of a kilometer or less in horizontal resolution. So what happened when we added this passive microwave radiometer, it was actually smoothing out a lot of the fine scale features. So more is not always better. And it's not just the number, but it's also the combination. So we were very pleased with this result. This is only a small subset. We're still running hundreds more experiments. There's a near infinite number of combinations and permutations of these sensors. So we'll never be able to run everything, but we have a nice sort of list and we're making our way through it. So as I mentioned before, we don't just have snow, but we have the full hydrologic cycle. So let's take all of these snow sensors and let's see what the impact was on the corresponding soil moisture. There it goes. You may see it in 10 seconds or so. But what we see is there is a cascading effect. And I want to point out that in this domain, the snow starts to melt in March or April. And that's when we start seeing our differences in the soil moisture. During the months of October, November, December, January, there's not a lot of melt. There's not a lot of change to soil moisture, except for at some of the lower elevations where it's seeing rainfall rather than snow. But after the melt season and early in the summer season, we do see some improvements in soil moisture. We can take a bunch of snow measurements. In this case, let's look at the C-band SAR and optical LiDAR. This is improvement in soil moisture due to improvement in snow. We got the better amount of mass of snow and the better timing so that during the ablation season and melt, it was more appropriate and more accurate in terms of the timing of the infiltration into the soil moisture and that change in response at the land surface. So we go ahead and continue to look, how does this cascade through the rest of the hydrologic cycle? Let's go into the soil where we are. What's the impact on vegetation? Again, the melt season is, yes.
Yeah, I'm sorry. Just when I interrupt you, that's when the slide comes to the correct number.
Thank you, Javeri. I should count to 5 after clicking and then start speaking, but thank you. So what we're seeing here is, again, the impact on modeled vegetation, in this case, leaf biomass, as a result of assimilating snow observations. So we got a little bit better snow at peak accumulation, and we got a little better timing of soil moisture. And so the vegetation in the model was able to turn on once it saw that moisture, and it was able to start growing more in accordance with the nature. So again, we can follow this cascading series of impacts from snow to soil moisture to vegetation, and again, keep track of that integrated cohesive response. And if you are really interested in the integrated hydrologic response, well, of course, we have runoff as part of our scenario. These are statistics relative to the synthetic truth. And what I'm showing here, it looks like for some of these scenarios, particularly all of the scenarios with the radiometer, the purple, which is the radiometer only, or this maroon dark red, which is the triple variant, including the radiometer, we see that the root mean square error timing of the runoff is actually degraded. So an improvement in snow or an improvement in soil moisture, as far as our model is concerned, does not always translate to improvement in other states or fluxes, but it does improve in some, but not always. So it's not a panacea, but we can study how the improvements are manifesting themselves, and we can quantify those in a very systematic and integrated format. We can do another type of experiment. So it's not just a question of what's the optimal combination, but for many of these sensors, particularly C-band synthetic aperture radar, I think the jury is still undecided exactly what are the retrieval errors. There's a lot more work to be done, and there's some debate as to what these retrieval errors are. In this particular scenario, we're assuming multiplicative retrieval errors, larger errors in deep snow. We do that for a variety of reasons. I personally think the errors are somewhere around 0.4, but we don't know what they are. So we run a large range, very high accuracy, very low accuracy, and we feel confident that we can bound reality. Reality is somewhere in here. I think it's about here, but we know we've captured it. We don't know exactly what it is, but what's going on here, as we see these different bars, we have increasing retrieval errors, low error, low error, high error. And we see as we have more and more error in our retrievals, we get less and less benefit in the model, exactly as we expect. And then the limit, as these retrieval errors approaches infinity, the common gain will actually shut down to 0, and there will be no assimilation. So this serves two purposes. It follows a trend that we expect, less improvement with larger errors, but it also allows us to ask the question, what level of error can we tolerate such that those retrievals are actually adding value to our model? Or in other words, how good is good enough? And the OSSI framework can help us establish an upper limit so that we could say, okay, our models need this or better. We need you, the retrieval and instrument designers, please figure out a way how to estimate snow from space with an error of this or less, so that when we incorporate it into our model and we get runoff and everything else that we care about, that these snow retrievals cannot give us, well, we know that we're actually going to improve our estimates of runoff if you can give us snow retrievals with this much error or less. So it becomes a very powerful powerful tool, not just to decide what sensors and how do we coordinate, but also what are the limits of the errors that we can tolerate in order to achieve our desired scientific benchmark. I think I'm running out of time here, so I'm going to speed things up. We've done some work on adaptive viewing. Again, if we could slew the sensor a little bit to the left or right? Can we see what we care more about? I have a master's student, Colin's, doing some very nice work on this. And these results are preliminary and he's making very good progress. But right now he can say that his algorithm, and this is just a single realization. We run many, many realizations, and then we take an average of the best, most likely realization so that the final path is much smoother. But what you're seeing here is rather jagged, and that's just a product of his search algorithm. But suffice it to say, it sees much, much more of the stuff we care about. We can apply this to irrigated areas. It sees much more of the stuff we care about relative to fixed viewing. We can apply this to snow cover climatology. It sees much more of the stuff we care about. We can apply it to vegetation disturbance. It sees much more of the stuff we care about. We can apply this to land surface elevation in the context of high elevation glaciers. We can see much more of the target that we care about. So we've got some hope on this. And just as a little video here, Colin recently put this together. The blue is the fixed viewing, and the red allows the sensor to slew a little bit. And you'll notice that the red, it's trying to maximize the elevation. And you can see that the red has a tendency to hug the spine of the Andes, all the way from Colombia down to Patagonia. It's not perfect. It doesn't do it everywhere all the time, but it does do a much better job relative to the static viewing. So we'll run an Aussie scenario with the static viewing. We'll run an Aussie scenario with the adaptive viewing with an adjustment of the errors. And we'll see if adaptive viewing actually adds more value. Is it worth the extra buck for the scientific value? And then finally, we're working to boil all of this down. No metric is the end all be all. So we, of course, we're running a lot of different metrics. I'm searching for the one. I would like to be able to boil all of this down to a single chart. I don't think I'm going to be able to do that. I probably will need three. I'll need one chart for systematic errors. I'll need another chart for random errors, and I'll need another chart for total errors. But imagine I could boil this down to one, and I'm using a normalized information content metric, and we're weighting it linearly where we're considering snow and impacts on soil moisture and impacts on vegetation and impacts on runoff. And we can see that some scenarios, if it's above zero, we're getting some improvement relative to no observations at all. If it's below zero, we're actually degrading the model. And in this particular example, it's because we have so many errors in our retrieval. We're running such a large error scenario that we're incorporating some of that noise from the observations into the model. So it actually makes things worse. But most of these scenarios are benefits. And by the time we get done with this, we hope to have hundreds and hundreds of points, most of them above zero, and maybe running this out to a combination of 4 or even 5 different sensors. But we're filling this in. We've got a nice framework. And any suggestions or comments you have on maybe making this easier to understand, I would love to hear. So the last bit I'll say, we're still working on this project. We're going to be going through this through the summer, so we still have a lot of work to do. But nature run's done, which means the synthetic observations are also done. Our open loop is completed, so we have a very nice benchmark for everything. We've run a bunch of univariate assimilation experiments, L-band radiometry for soil moisture only, C-band SAR for SWE assimilation only, vegetation LiDAR only. Now we're moving into the multivariate experiments. We're sort of layering these on top of each other. We can take 1 LiDAR or 2 LiDARs or 3 LiDARs and investigate the added utility of an additional LiDAR or an additional SAR or an additional radiometer. We are also exploring more and more nuances to our air characterization. In the beginning, we just assumed everything was uniform and isotropic, which is far from reality, but it made the math a lot easier. Now, when in the context of soil moisture, if you have a lot of vegetation, you're probably going to have larger errors. Or if you have complex terrain, you're probably going to have larger errors compared to a nice flat surface with no overlying forest. Same could be said about snow. Same could be said about vegetation retrievals, perhaps. So we're exploring this and we're adding more and more nuance. We still need to integrate the adaptive viewing. So we're running all these static viewing experiments. Currently on our supercomputer, we have our first adaptive viewing experiment. And to the best of my knowledge, we will be the first to conduct a land surface OSSI using adaptive viewing. I don't think anybody's ever done that. So I'm very proud of my group. We are pushing the boundaries in this project alone. And we have a very nice cohesive framework that we can use. And it's really amenable to a large range of terrestrial hydrology applications. And I left this last slide in because I recently was talking to some NASA program managers, trying to convince them that this is the greatest thing since sliced bread. And we pointed out that we've got a direct plug into a new project that we were awarded with Sujay Kumar from the Terrestrial Hydrology program. But this OSSI has numerous applications for the modeling and analysis and prediction program. We have a separate project where we're using lists as part of this new observing strategy. This is related to fire and actually using commercial satellite imagery and tasking it to adaptively go and collect the information we want that maybe the NASA satellites aren't collecting. We're also using this framework as part of a SNOWX experiment that is ongoing in Alaska. Hopefully COVID will cooperate and they'll be able to do the field work. The SNOWX has been shut down obviously for a couple of years, but hopefully things will be picking up. We're also using it as part of SOUP, the Snow Ensemble Uncertainty Project. And then finally, I see this framework as something really, really useful for space-based gravimetry. I'm on the science team for the GRACE follow-on science mission that measures changes in Earth's gravitational field and then tries to invert that to infer changes in terrestrial water storage. And this new mission, MAGIC, which I love these acronyms, they went ahead and just left out change, and then they used the A in and. It's hard to spell out a nice acronym, but the Europeans did a very nice job. And this is going to be a joint European-US program. What we'd like to do is the US would like to fly a pair similar to GRACE follow-on, and then we want the Europeans to fly a second pair so that now we would have a constellation of space-based gravimetry, which could really bring down the spatial resolution by a significant amount relative to GRACE follow-on, and also could potentially reduce the retrieval errors to something that adds more value to our model. So with that, I will stop and I say thank you for your time and consideration. I'm going to close my window because we've got some compressed gas delivery going on. I don't know if you could hear the beeping. But with that, I'll say thank you and questions, comments.
Thank you very much for your talk, Dr. Foreman. It was incredibly interesting. I know that we have a time constraint here, so I'll first go towards the audience questions and then I'll come to mine. We have a question, and it is about that we saw that by assimilating snow retrievals, we saw some improvements in soil moisture. So how do we know that these improvements in soil moisture are due to the improvement in snow?
Well, that's a great question. So we do have this scientific benchmark, and what we can see is that say, let's choose a particular year, there may be a negative bias in our open loop. And so we may have too little snow. So the assimilation is adding more snow, and it's carrying that snow season longer. So we're seeing melt and runoff much later in the season. In the open loop, all the snow melted and there was no infiltration. But with the assimilation, there's more snow, it lasts longer, there's more infiltration. And so we're really just getting the timing in the soil moisture and the snow melt. We're improving that by a month or so. And so we get a nice improvement in snow, and it lasts for only 2 or 3 months. Sooner or later, we get a lot of rainstorms, soil moisture sort of returns to this sort of quasi-dynamic equilibrium, whatever you want to call it. But the improvements on soil moisture are fleeting and ephemeral. And same thing with improvements to vegetation from snow. But there are improvements to vegetation from snow. And that's key. Again, often these are studied independently. So people are only looking at snow and they're not thinking about improvements to soil moisture or improvements to vegetation. But we're taking all of that into account.
Thank you for your answer. So another question is about the errors and parameters in the different runs. So when you are assimilating just one set of observations versus multiple observations at the same time, are the errors and parameters the same? And how are the error variances between these variables decided?
Okay, good question. I may be answering a different question, but we have not assumed any parameter uncertainty. We could have made model parameters random variables. We have this uncertainty estimation, but that just increases the dimensionality and we can never run all of these simulations. So we actually fixed the model parameters. And we do have model structure error, we do have boundary condition error, we do have parameter error, but it's sort of implicit and part of the total error that we can quantify by comparing our open loop relative to the nature run. Now, when it comes to error covariances, one of the fundamental assumptions of an ensemble Kalman filter is that model errors and observation errors are mutually uncorrelated. And then also the individual observation errors are also uncorrelated. So we left that alone. So our covariance matrix is diagonal. We could throw in some off diagonal terms, but our error covariance matrix is diagonal. And we just had to say enough is enough. It's a 2-year project. We can only push it so far.
Thank you for your answer. I'll just ask one last question. And this is perhaps when you were talking about the utility of these experiments. So could you comment on how we can convert these results into numbers or costs that you can show program managers?
Okay, excellent question. And I left all of that out. TATC, Trade Space Analysis Constellation tool that I overly reductionist refer to it as a space-time cookie cutter. It is much, much more. It has the cost estimator in there, and it's got the different, if it knows the weight and the power requirements, it will determine the propulsion system that needs to be used to place it in orbit. So there's a lot in there. There's also we're working on different utility metrics. Again, not my specialty, but there are some folks over in aerospace department at MIT. And then there are a lot of folks at NASA Ames and NASA Goddard that are making these developments. Paul Grogan, who was at Stephen Institute of Technology, he was a systems engineer, did his PhD at MIT. So he came out of that same group, and he's got a very nice group in New Jersey that is leading the charge. He's brought TATC into the cloud. Yeah, there's a lot that I left out, and I apologize for glossing over all of those details, but it's implicit in TATC.
So we know that there is a system in which we can get a cost estimate of these individual satellite mixtures as well. Yes.
As to the quality of that estimate, I will not say, but I will say there's a reason I did not present those numbers. And it's because I'm less confident in those numbers. I think we still have some work to do, but the goal is by project completion to have that.
Well, I'll stop here and thank our speaker again. If you have any further questions, please email me and I'll be sure to forward them to Dr. Foreman. Thank you again, Dr. Foreman, for joining us. At this point, I would request our audience to leave so we can just have a quick word with Dr. Foreman and thank him again.